Today we're going to do a very basic question regarding, you guessed it, gears. We have our input over here, and we have inertia for the gears, which we'll derive in a moment. But we have gear 1, gear 2, gear 3, all these gears. We have an idler gear 5, which shows that 4, this is like a car transmission, this is going to be reverse. I suppose this would be first gear, and this would be second. Basically, what this question is asking is, we have an input power from a motor on that input shaft of 30 kilowatts. And the input shaft, I should maybe put an I here to denote that this is indeed an input shaft of 1200 RPM. Now, the gear system is going to be meshing through 1, 2, 3, 6. So that's 1 up here to 2 to 3 to 6. So that's where it's going to be meshing. So we want to see what the output is based on that. Given our efficiency here, what we want to find is the output torque, the output angular velocity, the output power, as well as what is the equivalent system as seen by the input shaft, which we'll discuss in a little while. We'll discuss this inertia term right now. For inertia, we know that for a gear, the number of teeth is going to be proportional to the radius for a given gear pitch. So, radius is proportional to n. What we also know is that mass is proportional to radius. So m is proportional to radius. But how much of radius? It's radius to some power, is it not? As a matter of fact, it's going to be radius squared, but then we also have a thickness which we're going to assume to be the same. So this proportionality will hold as mass being proportional to the square of the radius. So we look at this inertia term and we find that inertia is proportional to mr squared, which is going to be r squared. So that's basically r to the fourth. So some proportionality r to the fourth. We'll do a constant. So I equals some constant times this n to the fourth. Number of teeth to the fourth. And that's going to basically tell us what our inertia is if we find that proportionality c. So that's what we're going to use to determine the equivalent system later when we are determining it. But for now, we're just interested in what's this output. So let's get started on that first. We have our input torque implicitly defined by the input power. So we'll call this A and we'll call this B. So our input power, P in, is defined as basically being your torque times your angular velocity. We know our angular velocity, and we'll have this T in. So why don't we say 30,000 watts equals T in, that's very messy, T in times omega in, and this has to be in radians per second. So we'll have 1200 RPM. We know that there's 2 pi radians per revolution, and we know that there's 60 seconds in a minute. And what we end up getting, that's going to be pi by 30, we get 30000 watts equals T in times 125.66 radians per second. So implicitly we now know our torque, our input torque, 238.74, and that would be Newton meters, which is a pretty high torque. Let's just draw out the gears that we know are there so that we have an idea of the system that we're working with. So here's our input. A little bigger. Here's our input gear. And yes, my gears look a little sloppily drawn. Go to here. output shaft, and there's our output. So here's our gear 1, gear 2, 3, and here's 6. So there's our output, there's our input. And we're given this efficiency of 96% at each interface. So here is 96%, here is 96%. And we're also given all of these teeth numbers. All we need to know is N1 equals 40, and that's number of teeth. So this gives us an idea. Our gear ratios are going to be defined as N2 over N1, we'll call that G1, and that's going to be 50 over 40, which is going to be 1.25. Next, we have gear ratio 2, which is going to be N6 over N3. I tend to do driven over driving for gear ratios. So this is going to be 40 divided by 35, which is about 1.14, say 29. And that's your gear ratio for G2. So your overall gear ratio, product of driving over driven, driven over driving. So overall, G equals G1, G2 equals 1.4286 is your overall gear ratio for this system. So that'll help us to figure out our angular velocity on the output, because we know that G equals N on the input, N on the output, which is equivalent to omega out over omega in, where omega is your angular velocity. What we see here, we have our gear ratios as being N out over N in, which I don't believe is the general convention. I believe driving over driven is the convention. But what we've defined here is what we're going to stick with for now. And what we need to do then is we say omega in divided by G is our omega out, because this formula here is 1 over G, which therefore omega out equals about 840 or 839.98 RPMs. So that's our output angular velocity from this. And we can convert that to radians per second the same way that we converted up there. This equals 87.96 radians per second. So what torque do we get? Well, if we want to calculate torque, we need the power. So let's get our power. We have the relationship already. P is equal to T omega. So on the output, we have T out equals P out over omega out. What is our power output? Well, let's take a look at this system. And as you can see, I kind of trailed along before I realized my small error. If we follow this power through this system, we see it goes in through gear 1. Between 1 and 2, we have some loss. Between 3 and 6, we have some loss. We don't have any loss between 2 and 3. And then we have the output. So we only have 2 places where we're losing efficiency, or where we're losing some power. And that's due to the efficiency. And since it's a series system, those efficiencies are going to multiply together. So basically, P out is equal to our input power, P in, times those efficiencies. So 0.96, and that'll be squared since they're both 0.96. And so our overall efficiency is going to be 0.92 0.9216. So taking this 0.9216 and multiplying it by our input power of 30 kilowatts, we get an output power of 27.648 kilowatts, which we can now take our angular velocity up there, and we can calculate, based on this, our output torque. So T equals 27,648 watts divided by 87.96 radians per second. And that gives us an output torque, 314.32 Newton meters, which is a fair bit of torque. So now, let's take a look at this theoretical torque. We had our T in equals 238.74 Newton meters. And we have this gearing ratio, which if we apply it directly without considering our efficiencies, then T out equals this overall G times T in. Since it's a reduction gear system, we expect the output torque to be higher. We get the output torque is actually equal to 341.1 Newton meters. So if it wasn't for these losses, we'd have a little bit of extra output torque. But since we have these losses, our output torque is only 314.32. And actually now we have our output angular velocity, we have our output power. That's everything we wanted for the first question. So now let's take a look at our second question, which has to deal with the equivalent system seen by the shaft, which is talking about our equivalent inertia. So now we're going to take a look at the equivalent inertia of this system. And what we're interested in is what the system at the input shaft is seeing. So we basically want to reduce the system down to this. Equivalent, just one gear on a shaft spinning. So we can basically say if we have an input torque here on this shaft, then what is going to be the response of this based on T equals I EQ omega, not omega, omega dot, I EQ alpha. So we want to know what this equivalent inertia is, what I EQ is. And the way we're going to do this is with kinetic energy. So based on our system here, we know we have gears 1, 2, 3, and 6. And each of these gears has an inertia. And in addition to that, we have these losses at the meshing interface. So from gear 1, we're seeing a little bit of extra torque from gear 2, a little bit from gear 3, and a little bit extra from gear 6. Based on this gearing ratio, we're seeing a little bit more resistance to motion. So this we would expect to go up, especially as we increase the number of gears on this shaft. So as we previously defined, we had said that our inertia, I, is equal to some factor c times n to the 4, the number of teeth to the 4th power. And we have some gears on the order of 50 teeth, which would be close to 6.6 million or 6.125 million when we take it to the power of 4. What we're going to do here is we're going to just assume c equals 1 over 6 times 10 to the 6. And we're not really assuming that, we're not given it. So we want to find the inertia. We're just going to do this so that we get reasonable values on the order of maybe 1 kilogram meter squared. Relatively reasonable if we're talking about a small system, maybe 10 centimeter diameter gears. So that's what we're going to be looking at here. So we have our C, we have our N from the teeth of these gears, which are defined above. So we can calculate our inertias. And just to simplify things, instead of going 1, 2, 3, 6, I'm just going to redefine this. This gear is now gear 4. So let's take a look at our inertias, which magically will appear down here. Wow, looky there. So there's our inertias that we calculate based on that. And we have our inertias for each gear now. So now, what we want to do is we want to calculate what the gear 1, what shaft 1 is seeing. So let's do our kinetic energy. It's hard to read. So for gear 1, kinetic energy of gear 1 is 1/2 I1 omega 1 squared. And the way shaft 1 sees it, that's exactly what gear 1 is. We don't know what omega 1 is. In this case, we're assuming we don't know omega 1. We don't know it. So that's one thing we're going to leave as an unknown. For gear 2, 1/2 I2, obviously, but we want it in terms of gear 1, in terms of this omega 1 squared. So we know what omega 1 squared is, but let's go back up here where we defined our gear ratio. And we found our omega out by dividing by g. Dividing our omega in by g, or in this case omega 1 would be divided by g. So there's our omega in divided by g. So let's divide our omega 1 by g. But it's squared, so we got to do 1 over g squared. Now also note, we're losing energy here. We're losing just that little bit of energy, which is going to add a bit more resistance to the movement. So we're also going to divide that by our efficiency. Since this is an energy equation, we need to account for that energy loss. And this makes sense. So there we go. We have K2. K3 is similar. I3 omega 1 squared, or this should be G1. 1 over G1 squared over eta. And finally we get to our gear 4/6, in which we have another efficiency and another gear ratio. So K4, or 6, equals 1/2 I4 omega 1 squared. We still want it in terms of omega 1, but now we're doing 1 over G1 squared, 1 over G2 squared. We also have 1 over eta, and since eta is the same for both of them, we'll just square it. But it's just eta times eta. Eta for the first one times eta for the second one. So now, what we want to do is we want to say the summation of the kinetic energy is equal to 1/2 equivalent inertia times omega squared. And we'll say omega 1 squared. And we still don't know what that value is, but do we need to know it? Well, take a look at this. Omega 1 is a factor of all of these and is a factor of this. So it looks like it's going to factor out. Let's see. We have common factor of 1/2 omega 1 squared. And the summation of kinetic energies, we're going to have I1 plus I2 1 over G1 squared eta plus I3 1 over G1 squared eta plus I4 1 over G1 squared G2 squared eta squared. And again, that's just a purely mathematical relation, equals 1/2 equivalent inertia omega 1 squared. So we see this common factor of omega 1 squared does drop out. And we now know our equivalent inertia as seen by the input shaft. So I equivalent equals we find an equivalent inertia of about 1.5147 kilogram meters squared, which makes sense. We would expect it to be larger. So what this tells us is if we have an input shaft here with a given torque, exactly how fast our angular acceleration is going to be at that instant, assuming no resistance, of course. We would have to calculate the resistance otherwise if we wanted to include it. But we know what this inertia is. Our inertia is c times n to the 4. We know what c is. So we can also calculate the equivalent gear, where we say n equals the 4th root of I over c, and we know what I is from here. We know what c is. So there's our equivalent. NEQ equals 4th root of I equivalent over c. So let's take the 4th root, and we have that 1.5147 times 6 times 10 to the 6. And we end up getting about 54.9, approximately 55 teeth, which is interesting, because this tells us that if we had an equivalent gear just spinning on a plane shaft, we'd have about 55 teeth on that gear to get the same inertia as all of these gears put together spinning at their respective speeds. So it's not just a summation of all the teeth, but it's a summation of the inertias, which gives you a very different answer, especially when you consider that number of teeth is to the 4th power, so a small change in number of teeth results in a large change in inertia. So for 55, we have, say our largest gear was 50, we may have only a 9% increase in the number of teeth over our highest number of teeth, but that results in a 41% increase in inertia just by having this small difference. And that's just basically all this does, is this tells us what the equivalent system would look like if we wanted to model it dynamically in terms of angular acceleration. So that's how our kinetic energy can be used to find our equivalent moment of inertia. So thank you all for watching. I'm Spider Pilot. If you have any questions, I'm sure you do, because I didn't really cover this as clearly as I might have been able to. Post a question. Post it on the YouTube channel. I'll be happy to answer. That's all. Gears! Gears! It's gears! Gears for the years!